The goal of this video is to introduce the Q Bottleneck tool from the Stanford-MIT Healthy Elections project. The tool is meant to help election officials understand the voting process at a single polling place where the process is constrained and how highly it will be utilized. It will also help those planners understand what will happen to the process when social distancing measures are implemented. This tool takes several things as inputs. The primary thing is the characteristics of the polling place, including the setup of the process, the time of each step, and the number of servers. It also takes the average voter arrival rate into account, and it allows for several different inputs regarding the impact of social distancing on the polling place process. We'll walk through each of these. If we scroll down to the tool, we'll see it's divided into a left side and a right side. The left side are the inputs, and the right side are the outputs. First, we select a system setup. By default, it's a three-step process: check-in, voting, and scanning. But we also have the option for a simpler two-step check-in voting process or a four-step health check, check-in, voting, and scanners process. If your process is slightly different, choose the one with the correct number of steps and ignore the row labels. For now, let's stick with the three-step process. We'll move down to the inputs. As a starting point, we'd recommend putting in 2016's data just to get a sense of what the voting process would look like if nothing changed. So for now, let's assume that we have at this polling place an average arrival rate of 40 voters per hour over the day. Next, we'll put in the number of stations and the average time to complete the task in minutes for each of the three steps. We'll say that there's 3 check-in booths. It takes 4 minutes. We'll say that there are 12 voting booths taking 6 minutes, and 1 scanner taking 45 seconds, which we'll put in as 0.75 minutes. To keep things simple, let's hit calculate right now to see what happens. You can click the calculate button here, or the one here down at the bottom. They both do the same thing. Okay, let's walk through what happened. The columns on the right of the table and the right side of the table have both been populated. For each row in our table, the tool has calculated the throughput at each step in voters per hour and has used the voter arrival rate to calculate the utilization of each step. And on the right, our inputs have simply been replicated. More on that in a minute. Here we can see that with the yellow exclamation point, the tool has also flagged the check-in step as our bottleneck because it has the lowest capacity in voters per hour. Only 45 voters per hour can move through this step in the process. That means that the utilization at this step, with 40 voters per hour arriving, is 89%, and we have lower utilizations for the voting and scanning process. The bottleneck at the check-in step means that we can expect lines to form at the check-in step and likely not at the voting and scanning steps. However, if we imagine a situation where voting takes 15 or 16 minutes, let's call it 15 and a half, and we'll hit calculate, we can see that the utilization of check-in and voting is very, very similar, which means that maybe we wouldn't be as confident that no lines would form at voting. But in our example here where we had utilizations that were very different between the bottleneck and the non-bottleneck steps, we can be reasonably confident that the lines will form only before check-in. A final thing to note is to be careful when the utilization of any step approaches or exceeds 100%. First of all, if we go to 46% or 46 voters per hour, we can see that the exclamation point turns red because there is not sufficient capacity to meet the voter arrivals. Second, it will make the utilization numbers less interpretable. See here that there's 38% utilization and 100% utilization, but if we increase this even further, those numbers don't change because the throughput of the system is governed by the bottleneck, which is completely full. So even if more voters arrive per hour, no more voters will be let through the system than the 45 governed by the check-in. We'll go back to 40 for the rest of the example. Next, let's include some social distancing measures to see what will happen. We scroll down here. In each row, we click on the checkbox to activate the input and then enter a number for the parameter of that input. First, this input means that we'll have fewer voting booths in the process. If a voting booth is in a bank of booths, and each booth is 2 feet wide, only every third booth can be opened while maintaining a 6-foot social distancing, meaning that we will have a 66% reduction in voting booths. For cleaning the booths, let's assume that every n voters, n is the number here, we will need to send in a fake voter to clean the booth, and they will clean the booth in as much time as it takes a voter to vote. Let's say that every 6 voters we send somebody in to clean the booth. Next, we can implement a longer check-in time. This may be because we have less well-trained poll workers, and/or we might have additional COVID-19 questions. In any event, let's assume that this is an additional 30 seconds. And finally, we can reduce the voter arrival rate by assuming that there's going to be some increase in absentee voters. In this case, let's say that 20% of our voters are now going to be absentee voters. If we click Calculate, now we see a different table on the right than on the left. Let's walk through what's happening here. First of all, we'll notice that the voter arrival rate has decreased from 40 voters per hour to 32, reflecting our increase in absentee participation. You can see that our check-in step will take longer to complete, and that has impacted both the capacity and the utilization. Finally, we can see a large reduction in the number of voting booths and an increase in the average time to complete voting due to the fake voter that we send in to clean the voting booths. Again, that's impacted the capacity and the utilization. And scanning has not changed. The capacity remains unchanged, therefore, but the utilization has changed because the voter arrival rate has changed. The yellow exclamation point is telling us that our new bottleneck is now the voting machines, not the check-in process. The throughput of the system has decreased from 45 voters per hour at the bottleneck to 34 voters per hour at the bottleneck. We've made up for this by having a lower voter arrival rate, but a higher utilization at the voting process suggests that it might be the case that we expect longer lines. There are other tools that will tell us about line length. Finally, let's see what happens when we introduce a health check. If we go back to the system setup and select this option, we have a 4th row in the table where we can implement a health check. Let's say that we have one worker who at the beginning will ask voters a series of questions taking 1.8 minutes. But because of this, we no longer need to have a longer check-in time because that's taken up by the health check. If we click Calculate here, we'll see a number of things have happened. First of all, this is our bottleneck in the original situation, but because the health check is happening during COVID, what we really care about is over here. It looks like there is enough capacity to meet the 32 voters per hour, but just barely, with a very, very high utilization of 96%. It's highly likely that we'd see long lines at the health check here. Additionally, the bottleneck has shifted to the health check, so it might be worthwhile to have a second person working the health check, and then our bottleneck shifts back to the voting booths in the change case, and in this base case over here on the left, the voting booth or the check-in process would still be the bottleneck here. Hope you found this video useful. Thank you very much.